we have Manogna Mantripragada. Manogna works towards building a sustainable tomorrow and advancing clean energy by addressing the environmental and equity issues through machine learning and AI. Her primary focus is using predictive modeling to understand the energy grid and forecast different clean energy scenarios. She's also a strong advocate for women in technology and works with WIDS as an ambassador for the WIDS Atlanta chapter. Manogna will present the following workshop: Baby Steps Towards Building Your First Machine Learning Model. Please welcome Manogna.
Hi, everyone. I am a data scientist. I work with Greenlink Analytics. We are a nonprofit organization. We focus on creating a sustainable tomorrow, looking at equitable and clean options for cleaning the grid or reducing the carbon footprint in the environment. So we regularly work with a lot of cool machine learning projects, get our hands dirty with the data, and have a lot of possibilities to explore different types of data sets and different types of modeling techniques. So today I'm here talking about how to build your first machine learning model, what are the baby steps, what do you need to take care of, and what do you need to keep in mind before you know your machine learning model is a good model. So, so quick overview here. These are the objectives. We're going to talk about what the machine learning model is. We're going to look at the different model building options. We're going to go through a few tips and tricks to keep in mind, the implementation, and next steps, and how do you want to move your model building techniques further? How do you get the data sets? How do you extract different data sets from various places? And how do you keep building the model? All right, so machine learning simplified. The entire machine learning modeling can be classified under two umbrellas. One is classifying, one is quantitative predictions. Be it supervised learning, be it unsupervised learning, you still have these two as the main categories. Reinforcement learning is a different ballgame altogether, so I'm not going to be covering that this time, but I'm talking about supervised and unsupervised, and we're going to talk about how we can classify them broadly into these categories. All right, so if model building was like cooking and you had to prep a meal and eat it real quick, so you just whip something up without too much thought into it, and when we start eating it, this is how we look. The baby is unhappy having that spoonful into his mouth, and they're like, nope, this is not something that I enjoy. But if we actually take effort, follow the steps, we can actually achieve a great machine learning model. I see a hand raised. Could we quickly take that question? If that's okay.
So right now, Manogna, I do not see any questions in the Q&A panel. So maybe someone pressed it by mistake, possibly.
Okay, yeah, sure.
We continue.
Yeah, and you can see the presentation, right? I'm just quickly confirming.
Yes, yes.
Okay, all right. So in that case, building it the right way is important. So what do you mean by building it right? There are specific steps in model building. The first one is defining your problem statement. This is the first and the foremost important piece of the machine learning modeling. You need to know why you're doing this analysis. It's not always about finding or predicting a model or finding to classify the data. It's about what the use case is. Where do you want to use it? A lot of times in the industry that I work with, the business does not really know what they need. So if they come and tell us, this is what we want you to do, but if you ask the right questions, the problem statement might be a little different. So it's always important to get your problem statement right before you even jump into the data. Next, it is data gathering. There are different sources of data gathering, which we're going to look in the next few slides. But this is where you start your data gathering, you build for building a strong model. Then you have EDA and pre-processing. This is the exploratory data analysis step. You would need to go through each and every data point to understand if this is relevant for your model or not. Do you want to keep it? Do you want to kick it out? And what kind of data do you want to start with and what kind of data do you want to put into your model. Like they say, what goes into the model? If it's good data, you get good results. If you don't have good data, good quality data, your results might not be as good. Then it's about baseline or dummy model. You need to build a baseline model, and we're going to look why is it important to build a baseline model before you even start picking or selecting or training and testing your models. Choosing your evaluation metrics, building a candidate model training. Candidate models are the different models that you can choose for your problem. For example, if it's a regression problem, you might have multiple models that will serve towards a regression problem. So how do you know which model is the right model? So that's how we go through a candidate model training. Then you have a model selection process. And how is the selection done? You need to keep in mind a few points before you know and choose a model. So that's what we will talk under the model selection. Hyperparameter tuning, cross-validation, model testing, and results. These are the fine-tuning. Once you have a good model in hand, you're tuning the model. So this is what we will talk in the end, and we'll talk how do you convey your results and how do you follow all these steps together. So problem statement. If you know this cartoon, it is a very famous animated series. It's there are two characters called Phineas and Ferb. They are young genius minds who want to do something in their summer. So let's just give them a problem in that case. So today's problem is going to be exploring trends in energy burden. So what is energy burden? Energy burden is the average household energy bills divided by the median income of a household. So higher the income, your energy bills, your energy burden would be smaller. But if you have lower income but higher energy bills, your energy burden is going to be high. So this is clearly given from this formula right here. You have the data points show two different states, Colorado and Georgia. We have across 4 different years. This is also shared with you in the form of a Google Colab notebook. Once you start opening and running the file, we can also go review this together in the end if you have some time, but you can also play with this and reach out if you have any questions in the end. All right, so get data. Where do we get the data from? Data gathering is a tedious process sometimes because not every time your data is readily given to you. Kaggle notebooks, Kaggle data sets are very clean, but real life data is not as clean. So data can be gathered from various types. These are just a few examples that I'm giving right here. Web scraping is one of them. You can get real-time data gathering. You can also use pre-existing data sets. And the data types can be of different formats. You can also have a tabular data set, images, text, audio, video, anything. So the data gathering requires attention as to what data you need. You might also require multiple data sources in order to combine and form this one strong, solid data set to do your modeling. So this requirement is tied down to the problem statement. If you understand the problem statement correctly, that's when you know, okay, one data source is not enough. I need to get 2, 3 different files, combine them together, form this final data model. That's where I can draw my analysis from. Then comes your EDA and pre-processing. After your data gathering, you would need to get the data, start cleaning it. So data cleaning has a bunch of steps. You can look at the missing values for the starters. Missing values create a lot of impact in your data. There might be a lot of missing values, there might be just very few, but it's important to address those missing values because they might change the distribution of the data. So there are 2 options. One, you can keep the data set or you can drop. I'll start with the drop. You can drop the column or the row when there are more than 70% nulls in that row or a column. You can just drop that. Or you can drop specific rows. But before dropping, there is always a requirement as to checking how does that impact your model. Do an analysis like, does this indicator have a strong relation with my target variable? If dropping this might make me lose information. If that's the case, then you don't want to drop the indicator. You might want to find a way where you want to treat this indicator, fill the nulls, and go on. So that's where the keep option comes in. Mean, median, and mode are the most common approaches when you take while filling on your missing values. But not every time these three options work the best. So there's always more options, and there's always an iteration that you need to go through before choosing which is the right way to fill your missing values. You can fill it using a column indicator saying that I have a column. You might create a one-hot encoding variable saying that this column, this row has missing, yes. This row is not missing, 0. So ones and zeros can be used as an indicator for the missing value. So this will also tell you if the column is important or not. You're not losing information, you're retaining the value, but in an easy way where you can keep track of how many are missing, how many are not. Forward fill and backward fill, these are useful for time series modeling because there is the component of time that plays a role here. You can't use a median value or a mean value, just fill the values because the previous timestamp has a impact on the next timestamp. So that's where your forward fill and backward fill approaches come into place. Building a regression model, you can use continuous variables. And for a logistic regression, you can use discrete and categorical variables. So you can build a regression model to find the missing values. So that's not your final model. This is an intermediate step. If you think this column is very important for you, and we cannot replace the missing values with just a hunch that this would work for us with a basic level of testing, then in that case, we can also build a regression model to find those values and impute them. The next thing for data cleaning is duplicates. It's also important to remove your duplicates or else your data would be biased, is what I can start with. All right, the next one is feature selection. In this case, it's important to select your features before we even step into building a model. So if we start with 100 features, not all 100 features are relevant for a model. So choosing a subset, eliminating the irrelevant and redundant features is a good practice to make a robust model where the model knows which indicators to pay attention to and which ones are not really important so that the noise is completely cut down. So on the left side, I have put down an example of a correlation matrix. This is a heat map. And if you look at this, it shows different indicators that might have an impact on my energy burden. And if I may take your attention towards the scale on the right, it shows that the lighter the color, the positive correlation, that means if that indicator goes up, my energy burden goes up. If you go down, the deeper the color, the negative correlation. If my energy burden goes up, the indicators goes down. So this relation is important to understand what indicators do you want to keep, what indicators do you want to remove from your data set. The next one comes in multi-collinearity. Multi-collinearity is a process where two indicators are so strongly correlated with each other that if one goes up, the other goes up too. And that's a problem because the model is trying to find relevant indicators to build a strong, robust prediction. But if all these indicators have strong correlations within them, the model will never be able to find the right indicator to learn from. So it's always important to drop or remove the columns with high multi-collinearity. We use a variance inflation factor that's called a VIF factor. This is implemented in the Colab notebook, but this can also be used to drop the values which have a higher multi-collinearity. I think the benchmark is like 10. If it's higher than 10, you have to get rid of the indicator. And automatically, if you run the VIF again, all the indicators values gets reset. And you need to do it till you have all the indicators which are like less than 10, the VIF factor. In that case, you know that there's no strong correlation between the independent variables. So your target variable and your independent variables can actually go into a training model and come out with a proper analysis because your training model will learn the right relation. Statistical significance, p-value. So a p-value talks about how significant an indicator is. The benchmark, the traditional benchmark is if your p-value is less than 0.05, that means your indicator is significant. If it's greater than that, you generally want to get rid of it or try using a different indicator in that case. So these three are one of the few steps that you can choose. Not every modeling technique would require all the steps, but it's good to try a bunch of them before we get rid of few indicators and retain few indicators. All right. Under the same pre-processing and EDA, there's a data transformation. Outlier detection is an important step in data transformation. So what's an outlier? An outlier is when you want to try to fit a line between the data points, but there's this one point that's so far off that when you put it into a distribution, it's completely skewed. So this graph you see on the left-hand side with these three distributions, the center one, the skewness 0, it's a normal distribution. But the positive skewness and the negative skewness are skewed towards right and left because there is a lot of data points towards the ends, that is the tail, and less data points between the center and towards the other side of the tail. And this is a problem because your data is completely skewed. And in order to learn those outliers, your model is trying to fit a line differently. So when you look at with outlier, the line is ill-fitted. Your error is going to be higher in order to accommodate for that one outlier. But once you get rid of that outlier, you see the fit is a lot more appropriate and it's more accurate. Your predictions are going to be accurate. But it's not always important to get rid of the outlier because outliers are important sometimes. You need to know why is it even an outlier? Is it something that the data needs? Is it something that you would need to do a little more research into to understand what happened there? Is it an outlier because that is a one-off situation? Is it because that is the trend there and there are not other data points that have captured that trend? So it's important to understand this distribution before getting rid of outliers and processing them. Next is scaling and normalizing the data. So once you have outliers and you realize, this outlier is something that I do not want, you get rid of it, you try to check the distribution again. And it's important to scale the model so that the model does not have varied values. If I have a column that has percentages, it's 90%, 70%, 60%, and the other column that is only in decimals between 0 and 1, it's 0.06, it's 0.9. So when the model is taking it, it'll give more weights to a column which has 90s, 80s, but it's not going to know it's in percentages. So it's important to standardize the data, normalize it if required. Log transformation is used to convert a skewed data set to a normal curve. So that's one of the approaches to normalizing the data. And you need to regularize the data so that the data is in the same format. The next one is balancing unbalanced data sets. So what do you mean by an unbalanced data set? So if I'm looking at a classification problem, a binary classification, and I have 100 data points where I'm to predict if it's going to rain outside today or not. And rain is depicted by 1, no rain is depicted by 0. I have 70 data points of rain and only 30 data points of no rain. So my target variable is an unbalanced variable. This is important to solve because when you're putting it into the model, when your model is training, it sees 70 occurrences of rain, 30 occurrences of no rain. So it's going to learn, if I give out a prediction that it's going to rain, it's going to be 70% of the chance is that it's going to be true. It's going to be correct. So my accuracy is going to be at least 70. But what about the no rain aspect? It's not capturing it. So it's important to balance the data set in order to get the true essence of the data where the learning is happening instead of just giving out a value because that's the trend it's seeing in the model. So there are two techniques. One is oversampling, one is undersampling. We can use these techniques to balance the data set before we go to the next step. All right, feature engineering. Feature engineering is now you've cleaned your data, you've normalized it, you've got it into the same format. you removed any outliers you have in the data set. Now what we see is we see a lot of categorical variables. A machine can never understand text. So that's the reason we go through a lot of hard work to convert the text into digits, a binary, or any other number format. So the same way, if there's a column that has a lot of categorical variables, it's important to convert them into a number format so that the model knows how to read it and how to interpret it. And that's what one-hot encoding is. If you look at this image on the top, there are 3 different islands. And what we're trying to do is we're trying to use the rows, we're going to convert it into a column. And we're going to assign a value of 1, where the value is for the specific column, and 0, where that row does not have that value. These will create a few extra columns, but this is important because the model will now know how to use this categorical variable column instead of ignoring it because it doesn't know what to do with it. Now, this is where I would again flag a quick red flag. There is a high chance for multi-collinearity in this place. So what happens is when you create a categorical column and you take it, you convert it to a one-hot encoding, you have 8 categories, you have 8 extra columns. You also have the categorical column. So you first drop the categorical column, you have 8 extra columns. All the 8 are so strongly correlated to each other because 1 in the first row means that 0 in the second row. So when you see the strong correlation here, it will lead to strong multi-collinearity. In this case, it's recommended that you drop 1 column and let the rest of the 7 stay, not all 8. Feature creation. Feature creation is when you want to combine a few columns and create one feature that would have more information than the old ones. This also comes into play when there's multi-collinearity. You want to drop a few columns and you're like, I don't want to drop these. These are useful to me. So in that case, we create a new feature, combine them so that even when you drop those columns, this feature has a lot more information in it. And instead of having those individual columns have an impact. Dimensionality reduction. This is another step where if your model has 300 features, it's difficult for a model to learn 300 features. Some of them are important, some of them are not. Feature selection covers a part of it, but now you're again left with 200 out of those 300. That's still a huge number. So what we do is there are approaches where you can reduce the dimensionality, just like in this small picture right here. The dimension from 3D gets reduced to a 2D and finally to a 1D. It's not going to lose information. It's going to retain the most important values in them, but it's going to lose the frill around it. So the extra information is what it's going to lose, but it's going to retain the most important features. So this is what PCA stands for. Then comes model building. So now we have the data, we cleaned it up, we processed, we are ready for building our model. But before that, we need to set the model ready in order to train it. So you need to create a test train split of your entire data set if there is no separate test data available, if there's just one data set. This is important because if you train your model and all the 100% of data, you would not know how does it perform when it's looking at an unseen data set. So just to avoid all the corner cases, we're going to build a model where we have a train validation test split. It's important to have a validation split as well, because when you're testing, that's an unseen set. But when you're training, do you even is working in the right way? So when you're training, you use the validation and train data set to test if your performance is good up to the mark and what you're expecting. And then the test data set is once you pick the final model, test everything out and you say, okay, this is the perfect model that I want to test out on my unseen data set. That's when you test it and see this is what the model performance is. So validation serves as an intermediate step in between before the test data is even released onto the model. The next one is evaluation metrics. Evaluation metrics are important. So how do we know if a model is doing good? We just see an accuracy? Not really. Do we just see the error rate? Again, that depends on the use case. If my model is a binary classification and my goal is to look at the accuracy, I look at the accuracy. But if it's about how many of those values which were marked as true have I predicted as true, so that's a different use case. And how many of them were false that I predicted as true, that's again a different use case. That you're finding your error, you need to know a different problem statement in order to find your right evaluation metrics. So there are a variety of evaluation metrics available for each model. It is important to know why you're picking it and how are you going to use it. So like I said, there is a performation metrics and there is an error metrics. So you need to pick the right combination in order to get a good performance out of it so that you can validate, verify, and move on. All right, now we've come to building a model, the meaty part of the entire presentation. So data cleaning took a lot of time, as you saw. We had to go through multiple steps. And that is what it is in the real life as well, because your data is not clean. You need to go through so many steps before you even get your hands on building a model. Building a model won't take a lot of time. It's just 20% of the time when you're like building the model. 80% of the time, you're just cleaning your data, getting your data, and processing it. So before we build a model, we start building a baseline model. This is called a dummy model. A baseline model is easy because it's the most simplest model. It does not have a lot of frills in it. You're not adding multiple layers or multiple leaf nodes so that it's not going too deep. It's just at a very simple level. It's trying to tell you if this is my input, and if your machine learning model is working on it, what would your output look like? What is your accuracy? What is your error? So it's easy to understand your data, different classes. If you have low signal in any one of the features, then you can go back and correct it before you train it again. It's faster to iterate. Some models take longer because your data is huge. Some models take longer because the model is big. So to avoid the hassle of you waiting for like 2 hours, sitting on a deep neural network, and once it runs and you're like, oh no, this is not the data that I wanted, going back and verifying your data set, it's always better to start with a simple model, which will tell you it's working for me, it's quicker, and your metrics are the right metrics that you choose, and the data is working. So now you can start getting into choosing different models. Next, so candidate models for training. So now that you have a baseline model, we've trained on it, we have printed out outputs, it looks good to us. So my input makes sense to me, my output makes sense to me. Now I know mine is a specific task and I want to build models. So there is no one specific recipe where you know that this model is going to work well for my data. It's never an option. So you need to try a bunch of models before you know which model works correct with your data. If linear regression works well with one data set, it's not necessary that it's going to perform the same way with a different data set. So when you try a bunch of models and when you print the results out, that's when you compare, okay, this model gives me a 60% accuracy, whereas the next model, a decision tree regressor, gives me an 80% accuracy. Random forest regressor gives me an 87% accuracy. So then you pick the highest performing model. So I have printed out a list of few options that you can choose for regression. That's a continuous variable, a logistic regression, or a classification model, and clustering. So once you choose a model, we have a model in hand and we look at it, it's working well for us, it's performing great, and we have an 87% accuracy. But now we want to verify if it's giving us a good accuracy for the right reasons, or is it giving us accuracy for a wrong reason? So that's where understanding the metrics, checking if there is any overfitting, understanding if there's a bias variance trade-off happening, takes the primordial importance here, because you need to know if your metrics are giving you the right result. and overfitting is not happening. So what is overfitting? Overfitting is when you have a training data set and the model learns it so much that it's trying to fit all the points in the curve. So it's not drawing a line, it's drawing a curve, a squiggly curve that it's trying to fit all the points in. And that you will see here on the left plot, the extreme right, last one, third one. See the overfitted model, your line goes through each data point. It's trying to go extremely squiggly. It's extremely fit to that data point. But this is overfitted because now when you use this model on a testing data, which it's not seen, it's not necessary that your testing data would follow the same path. It might be anywhere. So your error is going to be higher. Your performance is going to be lower. So in that case, you know that your training model had great performance, had the least amount of error. But your testing model had a great amount of error and no performance at all. So that's when you know your model is overfitting. And the trade-off is that the model should be able to give us low training error, high performance in the training module, low testing error, high performance in the testing module. So finding that sweet spot is what is important when you're training your model. The more complicated the model is, doesn't mean that the more better the model is. Sometimes it's just overfitting. All right, so what is a good model? A good model takes into consideration all the training points, but it's not completely fitting it. It's a good fit. And an underfitted model is, it just goes through it. There's a huge error, least performance, and it's not fitting it right. That's what an underfitted model looks like. But now, what is a bias variance trade-off? When we look at a model, we know that higher error, higher performance is not an option that we generally see. So you need to find that sweet spot, and that sweet spot is found using an approach where you stop the model from training and you print out the results and start seeing that the moment your validation error is higher than your training error, you stop it right there. That's where you start printing your outputs and seeing, okay, this is where it's stopping. There are different approaches, there are different libraries that are helping you do this right now, but this is something that we need to be cognizant about, where overfitting is a very common thing and it's sometimes not easily identified. The next option is hyperparameter tuning. Hyperparameter tuning is when we have the model. A model has different variables or different parameters that we can tweak in order to find a good way to improve the performance that it already has given. So once we use these parameters and we start tweaking them, we see subtle changes in the model, and they're different for different models. So if you're looking for a binary classification, or if you're looking for a regression model, you can go to the model webpage. You can see from sklearn, for example, if you're looking at an sklearn, you'll see different parameters that go into the model. Few of them you can change, few of them you cannot change. So the ones that you can change, you can start slowly tweaking them and seeing how your performance changes over time. If you print it out and plot it, you'll see that there is an optimized way where you stop it and you know that your performance is better, and you go more beyond that, it's going to deteriorate. So we quickly hyperparameter tune the model once we have a good candidate model ready. There are different ways. You do not know what number fits in. You can use a random search, give a range, an array saying that, okay, I have a binary classifier. I want to go to different leaf nodes. I don't know which number is the optimal number. My depth needs to be maybe 30, maybe 20, not sure. So you give an array and you let the model go in and do a grid search across each of them, do different combinations, and it prints out a result for you. So now you know, okay, this combination is giving me the best result. So you store that combination, save that model, and now you have a good model which has training and validation accuracies in the right place, which is ready for testing. All right. Cross-validation and regularization. So before we go to a testing phase, we have training and validation done. There's a different approach for validation, which is called as cross-validation, K-fold cross-validation. The image right here on the left side that you see are different folds. So what is a fold? When you have a data set, and I want to say, I want to divide it into five folds, or if I want to divide it into 10 folds, you take the entire training data, you divide it into 10 parts, along with your validation data, your training plus validation, entire set, you divide it into 10 folds. So now when you put it for iterations, the first iteration, it picks the first fold, uses it as your test data, trains on the rest of the 9 folds from second fold onwards. In the second iteration, it takes the first fold, the third fold, and goes on to the 10th fold as a training data, but then your second fold is your test data. So every iteration, it's moving your test data and picking a different fold so that all your data points are part of your training data set and also a part of your testing data set at the same time. This is an important practice so that we know there is no missing point in your data set that's not accounted for. It's going through an iterative process. You know, all your data points are covered. They've been trained well, they've been tested well, and you know the result that you see is not a one-off. It is a properly verified result. The accuracy that you see is the correct accuracy. Regularization, right? Regularization is a process where you're penalizing different indicators so that there is no high variance between them. So the moment I start model training, and if one indicator has a high variance, it starts completely shooting up or down depending on how my training goes on. So it's important to regularize, tune off the noise, tune in on only the features that are important. And once you do this, you would see that your model performance is more stable and it's not fluctuating every time we are running a different iteration. Right, so, oops. Model testing. Now we've trained a model, we have regularized, we have cross-validated, we have verified, we know it's a good model. Now we use the test data set, the unseen data set that we are trying to use this model, fit it, and test it onto. So once we test this model, after we tune the hyperparameters, we will see a few results that we've used the metrics for. We check the performance metrics and see how well the model performed. If it's up to the mark that we have expected it to perform, well and good. If not, we have to go back and repeat again the process where we tune things. We have to check what the issue is, look at the data quality, and make tweaks till we reach to a point where it's in a good shape. Sometimes not all models can give a 90% accuracy, not 99% accuracy. So you need to know why this is happening. Go back to your training model. Your error rate and your performance are going to be around the similar benchmarks. If your training accuracy is around 85%, the test is also going to be around the same range. It's not going to shoot up to 95%. So it might be a one-off case, but then it's not regularly seen that it's going to shoot up. So it's going to be in the same range. But what is a red flag is when it goes completely down. Your training accuracy is around 85, but your test accuracy is around 60%. That's when you knew there's something wrong that's happening. So you go back, reiterate through these steps, and you know, now you have a solid model, you test it again, and then you see, okay, this makes sense to me. This is an accuracy that I can work with. All right, so this image that you see on the right-hand side, this is one of the verification processes. This is called as a confusion matrix. I've posted a picture for a binary classification problem. So there is an actual class, that's the ground truth on the left side, and there is a predicted class. So there is something called as a true positive, a true negative, false positive, and a false negative. A true positive is when your actual data says that variable is positive. Your prediction is also positive. That means you are in line with what the ground truth is. So that's your true positive. Your true negative is when it's positive and real, but then you predicted it as negative. So that is a true negative. Similarly, there is a false positive and a false negative. So once you build this table for every classification problem, you would know what is your accuracy, what is the precision at which you can predict the true positives from the entire data set, what is the sensitivity, what is the specificity, what is the negative predictive value. So all these cater to different use cases. So these are, again, different verification metrics. You would need to pick which metric is useful to you. Not all are useful in the same modeling technique, or not all are useful in the same problem statement, but you would need to choose the right one so that you know you're building the right model. All right, now the results of the model. We have built a strong model. Your model is performing really well. You have a great results section. And now how do you deliver your results to the team? Not everyone from your team are going to be someone who knows how to read the data set, not someone who would know how to, what to make out of the accuracy scores. Or when you say, this is my metrics that I checked, and these are great metrics, I have great performance everywhere. Not everyone would know what it means. So it's important to translate your results into a visualization so that it's easier to explain and it's easier for the audience to hold and captivate their attention. Be it anyone, if you have the right visualization, you can easily walk them through, and it's easy to see the trends in a visualization rather than looking at the numbers. So I would always recommend take aid of some nice visualizations, not anything too fancy. Too complicated is also not something that you want to go towards, because if you're making a very complicated visualization, not everyone would again be able to read it. So you need to have simple enough, but that delivers and conveys your data. That's the right kind of the visualizations you need to choose in order to convey your results. The next one is acceptable margins of errors of the model may differ. So what this means is, for a medical healthcare data set that you're looking for, your problem statement is to find if this person has cancer or not. So in that case, your accuracy needs to be higher. Your false positives should need to be less. In example of COVID right now, we all have taken tests. There are so many times where we had symptoms, but then it came out negative. There were a lot of times where we had no symptoms, it came out positive. So you do not know which is true positive, true negative. So it's important to know these values in order to find how your model performance is. And sometimes the margin of error is less. When you're taking a modeling for understanding the life expectancy, so your scope of error is going to be very less. You cannot make mistakes there. Whereas on the other cases, your scope can be a little more higher than the other models. So it's always important to know what the margin of error is and how acceptable your model is performing within those margins. All right. Looking back, I know I've spoken a lot for almost 45 minutes, but I'm going to just quickly go through what we've learned. We've learned how to define the problem statement, how to gather, clean, and get your data prepped up. I know it's a very time-consuming process, but it's the most important process. You would see you're spending days together on getting your data cleaned before you get model.fit. So this is something I would recommend. Be prepared, invest a lot of time, learn your data. The more you learn your data, the more you can understand if your data is doing the right job or not. It's always important to know your data the right way. Explore the data visually if possible and pre-process before training. We also looked at how to select different matrix and how to create a baseline model, building and testing a model, and finally displaying the results. High-level takeaways from this. I would say model building is like building your own ice cream. You have a lot of flavors. You have different toppings on them. You have different cones, cups, or different options of what your base needs to look like. And each combination is going to give you a different result. So it's not a one-click attempt. where you just pick one and it works the best for you. It's a process where you make different options, you make observations, you choose different things, and finally you reach to a point where you like the ice cream that you created. You like the toppings, you like the base, and everything just works perfectly well. That is what a model building is. You have to go through multiple iterations. Identify when an ML model is required and when it is not. This is, again, a biggest concept. Not everywhere a machine learning model is required. Some places it's not. You don't need machine learning. It's simple analytics. You just need to create a dashboard. You just need to create some basic statistics to understand what the data is doing. You do not need to force a machine learning model to get the results out. So don't try to fit everything into a machine learning model. So I think that's a heads up that I learned the hard way. So I'm pointing it here. The next one is explore about pre-built model options. If you do not have a lot of time, there are a lot of auto ML options that you can use. You can just pick it, you can train it at a later point. You can try using those pre-built models. No model or no project is a failed project. You're always learning from the data set. If you think that I'm going to build this model and see if I'm going to use this in my to address one of the business use cases, and sometimes you realize that it's not really required after you put like too much effort into it, and that's common. You haven't failed at that project. It's not because the data was incorrect or something. It's because it's not required at that time. Maybe at some other point it will be required. So no project is a failed project. That's a biggest learning step here. And don't be afraid to get your hands dirty with the data. That's the last thing I would want to say. If someone wants to explore the next steps, they can always start with an existing data set. I would say Kaggle is a great option for your existing data sets. Registry of Open Data on AWS is another amazing platform. You have awesome public data sets. These are the links that I can post it here. I can send it across at a later point, but explore these resources because you'll get some good data sets here. Spend time on EDA and feature engineering. I can't stress enough on this. Try different approaches, read documentation. And finally, towards data science articles are something that have helped me the most. I usually go back, the explanations are great. And if you find something that does not work for you, you do not make sense to you, go back and read the official documentation. The official documentation has a lot of information that we don't really utilize. But if you read those documentations, it's going to be very useful when you're trying to build a model and improve the performance. So I know it's almost 2:48. I'm sorry to take so long, but thank you so much for attending. Any questions are mostly welcome here.
Manognya, thank you so very much for your workshop. I think a lot of us learned so much from the workshop, so thank you. And what we're going to do in the remaining time we have about 12 minutes left. We have quite a few questions for you. So I'm going to read the questions out loud. Feel free to answer. And we may need to defer some of the questions because of timing. So if we need to do so, feel free to do so, and we can always follow up offline. So here's the first question I see. Can you provide some examples of a problem statement that you deal with at work?
Like Louis explained earlier, I work in an energy domain. So I work mostly with cities and states. So what they try to tell me is they're like, okay, so for example, by 2045, if I want my city to have no carbon emission, how do I get there? And that's a very vague question. So you do not know if you're talking about just the energy plants, or do you talking about transportation? Like, do you want electric vehicles, or do you want to retire the other kind of vehicles? So that's where you start questioning more. You're like, okay, what kind of results do you want to see? Where do you want to implement? So I would say the person who's giving you the problem statement might not always be your end user. So always keep that in mind, that your end user might need this for a different reason. And for you to understand the question, probe more questions and get to the core of why do you even need to do it, so that you can actually cater to the right audience and not just put so much effort to do this analysis and then you're like, oh no, this is not what I really needed.
This is great. And I think one of the items to be mindful of is, think about your audience, think about the end results. that we're trying to seek. This is great. Okay, one person was very enthusiastic about your heat map or heat maps. So how did you create those heat maps?
Yeah, so Matplotlib and Seaborn are the two libraries which have amazing visualizations. So if you look at sns.heatmap, that's a Seaborn library that has a direct heat map that you can like use your correlation matrix. You can put it onto and have a nice display. You can change the colors, you can change the tones and everything. So that's a great way to customize and play around with it.
Great. Okay, so I'm just looking at time. So trying to get to quite a few of these questions and then, have some time to end our workshops. So here's this next question. If we have a lot of data, I mean, big data, even after the pre-processing, then what's the best way to make initial predictions? For example, a distribution / model about that data.
Okay, so that depends on what you're trying to do. Are you trying to understand what's in that data? Are you trying to get a feel of how the data is spread, what the distribution is? In that case, I would recommend doing initial statistics. If you want to see how well can this data be used in a prediction model so that I can find my target variable, is this data sufficient to get to that point? Then I think use a most simplest model. Just like I said, create a baseline model, put it into it and see, does it even predict? Like, are these sufficient to start with, or else do you need to go find more data?
Absolutely. And would you also say part of that too is more than likely the person will go through an iterative process. You start at your baseline and continue from there.
Yeah.
Perfect.
Yeah. It's always a long process to getting to the right fit.
Exactly. And here's this next question where the person asks, is there a correlation threshold that we can use to determine whether to keep or drop a feature?
Yeah, so that's a great question. So I would say anything above 70% is a good place to keep, because if you have around 200 indicators and there are only like 40 or 20 indicators that make sense about the 70% benchmark, you would still have a good data set. Anything below that, I think you're risking and you're trying to keep it. But then again, I would say, if you want to ask specific questions, like I want this column and trying to understand the relation between this specific feature with my target variable, then you would need to keep it and try to find a way how you can make that work with the model. So that's always important to go back and see, okay, what do you want to find? Like, for example, I had a use case where I had to understand the impact of health conditions on the energy burden. I have it in the Colab notebook that I shared. So it has a lot of nulls and I cannot use it, but then I needed that because I wanted to find the result. So I found a way so that I can keep it, pre-process it, and use it in the model. So I think that's important for us to find there.
I agree. And let's see. So try to get in at least 2 more questions because we have to finish up the overall session. So here are 2 questions that I think are probably relatable for a lot of the people in the audience. So how do you balance the unbalanced data?
That's a great question. And you would see that happen a lot of times. So there are different approaches. Like I just suggested 2 different approaches, something called as oversampling and undersampling. But apart from that, you have many more approaches that you can take to balance your data set. And this one that I'm talking about is for the target variable, but then there are different samples where you can like use the exact number of samples for the entire data set, try to train it so that you're not having different variations in your variables. So I can share with you all a list of different approaches if that's helpful. But yeah, on top of my mind, I have these 2 that I showed it in the slide.
Perfect. And one more question, and then we're going to close out the overall session. So here's the last question. Any of you that still have questions, we will definitely try to follow up after the end of these workshops. So here's this final question. Is oversampling the same as overfitting?
No, that's a great question. That is not. Oversampling is in an unbalanced data set. If I have column A that has 8 different values and then column B only has 2. So I am oversampling it. I'm increasing, I'm creating a simulated samples so that I match my target variables at the same level. So that I have 5 reds and 5 blacks if I have to choose between a red black ball or a black ball. So that's what oversampling is. Overfitting, on the other hand, is when you have overtrained the model so much that it has memorized your training data. It does not know that there is something beyond this training data that can even come here. So when it sees an unseen test data, it's like, wait, what is this? I don't know what to do with this because my model is so fit with all those data points in the training data that the test data will give you super high errors and super low performance with the model. So that's what overfitting is. I hope that helped answer the question.